Welcome. Today we'll try to touch the infinity. Geometric distribution will be our guide. Last time we established that the probability of geometric random variable taking value k is equal to probability of one successful Bernoulli trial times the probability of k unsuccessful Bernoulli trials. We call this general formula probability distribution function because it effectively describes probability of any value k in the whole distribution. We also calculated probability that the value from geometric distribution will not exceed a certain number. We call it cumulative distribution function, as it accumulates probability to the certain point of distribution. Both functions give us the same information, that as we increase our target result k, the probability of achieving it goes to zero exponentially fast. Let's see if we see the same result in R. Let's generate a sample of n equal 10,000 observations from geometric distribution with parameter p equal to 0.3. To do that, we use R geom function with arguments n and p. If we look at the histogram of the generated vector, we indeed see that the probability of getting high results goes to zero exponentially fast. Is it possible to resist this convergence? We know that if we increase q, the probability of high results will also increase. So let's do that. Let now p be 0.1 and q 0.9. Let's regenerate the sample and look at the histogram. We see that the histogram looks similar with the exponential decrease. However, the scale is different. This time it goes up to 100, whereas previously we only had 30. Let's go back to our vector and see what is the maximum observation. To do that, we just write max of R. 97. Okay, it makes sense that with lower probability of success, it takes more time to get a successful trial. What happens if we increase the sample size to 1 million? Let's regenerate the sample and see what is the maximum value. The maximum value increased. Why is that? We just simply have more observations. And even though the probability of getting 129 is very, very small, it still can happen in a very big sample. Let's try to push this number to the limit. If I want p to be very small, I do the same trick as with the very big. P equal to 1e minus 5 will give me 10 to the power of negative 5. Let's regenerate the results. That is 1 million. Pretty big number. But I want more. let p be equal to 10 to power minus 10. And what's that? R says that we produce some NAs not available. Let's look into our vector. Let's take first 20 observations. It looks like P is already so small that for the most of the observations in our vector, the loop does not give us successful result, and the execution is interrupted. If we just write max of R, the answer will be NA. We need to tell R to exclude NAs and just look at the numbers, like this. To do that, we need to include additional argument in the max function, na.rm, for remove na equals true. Okay, so now the result is 2 billion. Nice. But can we go to infinity? Well, not numerically. There is a limit to what we can do in R, and it is called machine epsilon. It is the smallest possible number. In absolute terms, our computers can handle for a number of type double. To get this value in R, we write dot machine $, double eps. It is of the order of 10 to the power minus 16, so pretty small. However, since we can't have probability smaller than this, we also can't go to infinity using R. But we want to know what would happen if our probability goes to 0. Will we ever get successful trials? If so, how many times? Or perhaps there is a limit to the geometric distribution. If so, what is it? To answer these questions, we're gonna need some real math. I will see you in the next episode, where we will answer some of them.